So Jupiter has the biggest, most beautiful, most energetic aurora in the solar system, which makes sense, right? Because Jupiter's the biggest planet, and you figure if the aurora on Jupiter's made the same way as on Earth and on Saturn and everything, then it should just scale how energetic your aurora are with how big your planet is. Because surely the aurora on Jupiter is made exactly the same way as the aurora on Earth is made, right?
Nope.
So it's long been suspected that Jupiter had an aurora because in the 1950s, with the advent of radio telescopes on Earth, people were observing everything they could with radio telescopes, and one of the first things they did observe was Jupiter and found a very strong radio signal suggesting that it had a very strong magnetic field, and magnetic field is what gives us our aurora on Earth. And that was confirmed then at the end of the 70s in 79 by Voyager 1 as it did its flyby of Jupiter and actually imaged the aurora for the first time on the poles of Jupiter. So because the aurora was so bright and so energetic, like they were actually emitting in the UV part of the spectrum, the ultraviolet, they're that energetic, you can't actually see them with the naked eye, that it was due to Jupiter's incredibly strong magnetic field that was causing it, because it's because of Earth's magnetic field the reason that we have the aurora or the northern or southern lights. What happens is that very energetic charged particles that are burped up by the sun occasionally stream out into space, and because they're charged they can't travel through the magnetic field without getting their paths curved, and so some of them are actually funneled down the magnetic field lines of Earth to the north and south pole. And when those energetic particles hit the Earth's atmosphere, they interact with the air, the molecules in the Earth's atmosphere, so whether that's oxygen or nitrogen, and they cause the electrons in those atoms to get a little bit excited, jump up an energy level, and when they drop back down, they always drop down and emit energy in the form of a photon, i.e. light. And that light always has exactly the same energy because the difference between the energy levels in the atom is always exactly the same. It's like a quantum fingerprint, if you will. And so it's always the same color. That's why you get those very specific colors in the aurora. You know, you get the red because of the nitrogen and the green because of the oxygen. And that's how we're familiar with all aurora across the solar system being formed, because like that's the definition of an aurora. It's something we call a discrete aurora because you get energy or light out from the particles in the atmosphere at very specific energies or wavelengths or colors. And so it was assumed that that's how the aurora on Jupiter were formed as well. That was up until the Juno mission. Now, the Juno mission launched back in 2011 and it entered a polar orbit around Jupiter in 2016. And basically its mission is to study Jupiter and its moons in a similar way to what Cassini did around Saturn. And it's a really exciting mission. It keeps bringing back amazing images of Jupiter, including the dolphins in Jupiter 1 that went viral a couple of weeks back, and also this really recent one of the shadow of Io on the surface of Jupiter that I talked about in last week's Night Sky News video. If you haven't seen that, check that out. But now it's in this polar orbit. One of the things that Juno was tasked to do was to study the aurora on the poles of Jupiter. Now it's orbiting Jupiter incredibly fast, like 100,000 miles per hour. So it actually swings over the poles in just a few seconds because it comes back again a little while later to observe them again. So there's a lot of data now from the Juno mission about Jupiter's poles. And so one of the first things that was published in 2017 by Mauk and collaborators was about the aurora on Jupiter. And what they were looking for were those discrete energies that the aurora of Jupiter were being emitted at. Of course, there'll be this sort of like background UV light that's sort of sunlight reflected off Jupiter as well. But there should be very, very large, very obvious, discrete bumps that they should see. What they found was that those discrete bumps were only there 50% of the time when the aurora was visible. Interestingly, there's also an extra little streak next to the aurora at all times as well, which actually comes from Jupiter's moon, Io, that I mentioned earlier is casting a shadow on its surface. Io is incredibly volcanic and it puts a lot of charged particles out into space that then get again funneled by Jupiter's magnetic fields down to its pole, causing its own sort of little mini Io aurora as well. What they found was that the aurora were always there on Jupiter. You know, you didn't need this like fresh influx of charged particles from the sun like we tend to have on Earth, where, you know, you'll see sort of a news flash saying, oh, there's been a big sort of charged particle ejection from the sun, like look out for very strong aurora, maybe even further south than we're used to, you know, when you see in the news. This was there all the time, and it wasn't at these discrete energies. It was, they were detecting it like really, really broad energy swath from the aurora on Jupiter, which is really strange. That's not how we're familiar with aurora at all. We're familiar with them at these very specific energies. So what's causing the aurora on Jupiter? It suggests that Jupiter itself is the cause of its own aurora. Now, the best hypothesis we have at the minute to describe what we're seeing here, and bear in mind, it is a hypothesis, it's not accepted theory, is all to do with the differences between Jupiter and Earth. The top of the atmosphere of Jupiter is very different to Earth. It's actually encased in what we call a plasma. Now, plasma is what we call like the fourth state of matter. You know, you have solids and you have liquids and you have gases. Plasma is very similar to a gas, but instead of having electrons bound around protons to make atoms, those particles are just separate. And so you have charged particles sort of floating around in this plasma layer at the top of Jupiter, which is obviously also spinning with Jupiter and spinning with its magnetic field, and all those charged particles are going to be affected by Jupiter's really, really strong magnetic field as well. So you have a very turbulent top of the atmosphere on Jupiter. So our best hypothesis of what's going on is that these charged particles in the sun are essentially being trapped in that top layer of atmosphere, and they're sort of catching the waves as the planet rotates and catching the waves of magnetic fields as it rotates as well. And they're slowly being accelerated to higher and higher energies, producing this incredibly bright ultraviolet glow across a huge range of ultraviolet wavelengths or energies, explaining A, why the aurora are so bright, and B, why the aurora on Jupiter are always there, because you've always got these trapped particles in there as well. So you can think of it as, instead of a discrete aurora, it's like a broadband aurora that Jupiter has. But this is still just a hypothesis. Juno has been observing since this result published in 2017 by Mauk and his collaborators, and we're still no closer to understanding what is going on in these broadband aurora of Jupiter. But these ongoing observations should eventually help us understand this unsolved mystery. But at the minute, it's 2019 and we're still none the wiser. And it was assumed that because the aurora, and this is how we're familiar with all aurora across the solar system being formed, and it was how Jupiter's aurora, what is with that word? Sanctor, baby blue, sanctor, baby. No, I don't have Wi-Fi to live in the Juno. I do have 4G to live in the Juno Mission. I don't have Wi-Fi yet. We just moved house and we don't have Wi-Fi yet, and I'm struggling, let's put it that way. What's actually going on in these broadband aurora? Oh, that was so loud, I'm so sorry. Yeah, Jupiter's cool and everything. All you Jupiter stands out there, but Saturn's still my favourite, sols. Thank God, baby.